when we learned about the photoelectric effect, it said in its most basic form, when light or a photon strikes a metal, we get an electron that's ejected. That is, if we're above the threshold frequency and so on. And of course, the properties of the electron can change depending upon the energy of the photon, and the number of electrons can change and so on. But in its most basic form, a photon causes an electron. This provided evidence for the particle theory of light. Right? If we don't have light as a particle with a certain quantum of energy, then we don't have an explanation for the photoelectric effect. We talked about diffraction, interference, polarization, and refraction being evidence for the wave nature of light. The photoelectric effect is evidence for the particle theory of light. Well, yesterday we started talking about the Compton effect, which in some ways is similar to the photoelectric effect. When a photon, a really, really high frequency or high energy photon strikes a metal, then an electron will be ejected. But we also get a second photon that's ejected as well. What do we know about that second photon as compared to the first photon? Yep, it's lower energy. Now, classical physics would have predicted that it wouldn't be lower energy. Classical physics would have predicted that if we were going to get another photon out, then it would have been the same photon as we started with, right? If a car runs into another car, then the two cars that come out of it are the two cars that went into it, right? We don't get a different car coming out of it. Classical theory would have predicted that this electron produced, this photon produced exactly the same as the electron that we had before this whole thing happened, exactly the same thing as the photon, exactly the same photon as we had before the whole thing started. But it wasn't. The photon was less energetic than the first photon. So Compton explained that, or at least he attempted to explain that by saying that this is really just a collision, like a collision between two cars at an intersection. But this time we've got a collision between a photon and an electron. Well, that's fine. It seems to work, except that it gives us one big problem, and that is that it assumes that photons have got to have momentum. And of course, photons don't have any mass, so how do they have momentum? Right? Usually we say the momentum of something is m times v. Don't have any mass, we shouldn't have any momentum. Well, this is the equation that describes the momentum of something with mass, but we learned yesterday that there's two more equations that describe momentum of things without mass. We derived those equations yesterday. We won't derive them again. I'll just point you to the top right-hand corner of your data sheet and remind you that those two equations are E is equal to P times C. The energy of the photon is equal to P, the momentum, over the speed of light. We could, by the way, replace E with H times F, which is the energy of a photon. But we also know that P, the momentum of a photon, is H over lambda, also on your data sheet in the top right-hand corner. Now, there's another equation as well, much, much harder to derive, and it comes not just from energy, but it comes from the law of conservation of energy and conservation of momentum. And it looks like this. Delta lambda is equal to H over MC times 1 minus cosine theta. H in both cases is the joules seconds value of Planck's constant, 6.63 times 10 to the minus 34. M would be the mass of the electron, and C would be the speed of light. Theta is a scattering angle, but not just any scattering angle. Some people like to measure the angle of the electron. It's the scattering angle of the photon. So whatever angle the photon scatters at. Somebody in the last class asked a good question, said, is that kind of like the angle when we're talking about diffraction and interference is measured from the central max? No, it isn't. Okay, it's like we've got a collision between two vehicles here, and we analyze it using the law of conservation of momentum. Okay, we're talking about the scattering angle of the cars in that collision. Here we're talking about the scattering angle of the photon in this collision. Does that make sense? Now, it looks like this equation right here is completely different and separate from these two equations. And you know what? Often it is. Often we're going to use the first two equations together, and we're going to use the last equation separately. But those two equations can come together. Okay, if we have, let's say, a question that asks us for, let's say, the final the final wavelength of a photon when it was scattered at an angle of whatever. Then we're probably going to use this equation, right? Well, if we were asked for the final momentum of that photon, then we would probably use this equation to find the final wavelength, and then turn around and use this equation to find a final momentum. So although they don't often get used together, occasionally they do. They look like they should be separate from one another, but they're not. Okay, they're all applicable together, just like in physics 20, all those acceleration equations that looked different from one another really went together. All right, we had 3 questions for homework last night, and I want to look at those 3 questions now based on the 3 equations that we just had up on the board here. Questions 1, 2, and 3 on page 723. Any issues with any of those questions? Number 3, okay. Any others? Okay, let's take a look at number 3. It says if a 10 nanometer X-ray is scattered by an electron, becomes an 11 nanometer X-ray, how much energy does the electron gain? Well, let's find the energy of the first photon, the first X-ray. Let's find the energy of the second photon, the second X-ray. We're going to say 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 10 times 10 to the minus 9. And we're going to get an energy there. That's going to be in joules. We're going to do exactly the same thing with the energy of the second photon. It's going to be in joules. And then we're going to subtract it. That's going to give us the energy that's gained by this photon as it's scattered through that angle. Does that make sense? Now, what would you expect here? We have an increase in wavelength, right? We go from 10 nanometers to 11 nanometers. What would you expect for an energy change? A positive value or a negative value? You can see the answer here. Okay, we can see the answer here, but what would we expect for the energy of the electron? Should it be positive value or negative value? Actually, it says a gain, right? Should be a positive value because it's a gain, right? But didn't we say that the energy decreases? Like if we go back to the Compton effect here, didn't we say that when a photon strikes an electron, the electron is produced and a second less energetic photon is produced? How do we get a positive value for the change in energy there? How do we get a gain of energy when we said we should get a loss? When we do this work here, when we find both of those energies and then we find delta E, it doesn't work out to be positive. E2 minus E1 works out to be a negative value for change in energy. So why are they saying that we're looking for a gain in electron energy? Why are they saying the answer is positive 1.8 as opposed to negative 1.8? Good, Caitlin. When we do this, we're finding the change in energy of the, when we do this analysis here, we're finding the change in energy of the photon. What are we looking for? The change in energy of the electron. Good. So the change in energy of the photon will be negative, right? The photon loses energy. It's got to lose energy because the electron that was not moving at all, it was just sitting there, has gained energy. Okay, when we talk about the Compton effect, we say a second less energetic photon is produced, but that electron had no energy to begin with, and now it's got energy, so it's going to gain energy. The photon loses, the electron gains energy. Does that make sense? Even if you miss that, if you don't catch that, you're probably going to still get the right answer to this, because you're going to end up with a negative value for delta E, and then you're just going to say, oh, I'll just drop the negative, and you'll be right. Okay, but we want to understand that as well. Okay, I want to do another example here. Page 724, it says an X-ray, a photon 0.0500 nanometers, scatters at an angle of 30 degrees. What's the wavelength of the scattered photon? Here we're probably going to use that third equation that we learned yesterday. Delta lambda is equal to h over mc times 1 minus cosine theta. So we get 6.63 times 10 to the minus 34. We're always going to use that value. The mass here is the mass of the electron that's ejected, times c, which is the speed of light, 3 times 10 to the 8 meters per second. Theta is 30 degrees. All right, that seems easy enough, right? Let's do this on our calculator to make sure we can all do it. It's not that hard, but say 6.63 times 10 to the minus 34. Divide it by, do some brackets on the bottom here, 9.11 times 10 to the minus 31 times 3 times 10 to the 8. That number is always the same. I don't know why they don't just make that a constant. Like, let's call it a constant x, and then just use that number instead of having to write in these every single time and do the calculations every time. I don't know why they don't do that, but they don't. So we're going to have to find that every time. Let's multiply that by 1 minus cosine 30 degrees. Make sure you use brackets properly here. Cosine 30 and the bracket again. And I'm left with 3.25 times 10 to the minus 13. Is that my answer? No, it isn't, is it? Caitlin, what is it? What do I got to do? Yeah, that's the change in wavelength. I got to find the final wavelength. So let's say delta lambda is equal to lambda f minus lambda I, and then rearrange it to solve for lambda f. What would we expect to get here? A bigger value or a smaller value than the initial wavelength? If the initial wavelength is 0.05, the final value should be smaller or bigger. The energy of the photon decreases, the wavelength of the photon increases. Wavelength will go up, energy will go down. And when we look at this rearranged equation, we can see that, right? It's delta lambda plus another number, plus the initial value. And I'm not sure what we get there, but you can see how we do it here. What if the question didn't ask you for lambda f? What if it asked you for the final momentum? Well, then you do exactly what you just did, and then you'd say P is equal to h over lambda to find the final momentum. Try at your desks just one problem that goes along with that on page 724, please. All right, if we're okay with that question, I got one more to do with you here. And this doesn't go with any practice problems, so you'd be happy to see that we're just going to do it as a group, and then you don't have anything to work on after this. Page 723, it says, what's the maximum change in wavelength that a 0.010 nanometer X-ray photon can undergo by Compton scattering with an electron? Does the initial wavelength in this example matter? What's the maximum change in wavelength? Okay, we haven't learned to find the maximum change in wavelength, so what do we got to do? We got to think. Okay, we got to think a little bit. Okay, where might we start? Well, we know how to find a change in wavelength using the equation delta lambda is equal to h over mc, right? Delta lambda, h over mc times 1 minus cosine theta. So let's write that down because it's the only thing we know right now about finding a change in wavelength. Now, we've pointed this out before, and you've probably noticed it as well, that h is always the same, and m is always the same, and c is always the same. So that number that appears in front of the 1 minus cosine theta, we'll call it the coefficient that appears in front of 1 minus cosine theta, is always the same value. Nothing we do to that changes that value. The only thing here that will change the delta lambda is the angle, the scattering angle. So let's try a few different scattering angles and see what happens. Okay, I don't want to try 30 of them. I want to try a handful of them. Let's try 0 degrees. Let's go 45 degrees. Let's go 90 degrees. Let's go 180 degrees. And let's see what effect that has when I try these different angles. So, regardless of what angle I'm using, I'm going to have h over mc, whatever number that works out to be. I think it was 2.45 times 10 to the something, times whatever's inside the brackets. Basically, what we're saying here is that we want to maximize this number inside the brackets. What angle do we need to use in order to maximize that angle? Let's figure it out. Let's say cosine 0 degrees is equal to what? You guys know this? If you don't, then punch it into your calculator. Okay, give me a value for cosine theta. Matt, do you have it? For cos 0, yeah. Good. Cosine 0 is 1. If cosine 0 is 1, then 1 minus cosine 0 is 0. Make sense? 1 minus 1 is 0. Well, if this number inside the brackets is 0, then whatever that number is out in front, h over mc, it doesn't matter because that number times 0 is 0. That's not going to maximize delta lambda. It's going to minimize delta lambda. That's going to give me a delta lambda of 0. Right? Anything times 0 is 0. Let's try 45 degrees. Cosine 45 degrees is 0.707. 1 minus cosine 45 degrees is going to give you somewhere in the range of 0.3, 0.293, I think it is. So now inside the brackets there, we've got a value of 0.293. 0.293 times h over mc is bigger than 0 times h over mc. Would you agree with that? Well, then the first one can't be our maximum value then, can it? Because we've already exceeded the value that we did with 0 degrees. Let's try 90 degrees. Cosine 90 degrees is 0. 1 minus cosine 90 degrees. 1 minus 0 is 1. All right. Well, 1 times h over mc is bigger than 0.293 times h over mc. So this one's gone now. That one can't possibly be our maximum because that value of theta of 0 degrees, sorry, of 90 degrees, gives us a bigger value of 1 minus cos theta, which gives us a bigger value of delta lambda. Let's try 180. Cos 180 is, anybody know that? Negative 1. 1 minus cosine 180, 1 minus negative 1 gives me 2. Well, now I've got, inside those brackets, I've got 2 times h over mc. That's the biggest value that I can possibly get for delta lambda right there, is h over mc times 1 minus cosine 180, because it's the same as saying h over mc times 2. And everything else gives me a value of h over mc times something smaller than 2. So to solve this question, what I really want to do now is say, scroll down a little bit and say delta lambda is 6.63 times 10 to the minus 34 over 9.11 times 10 to the minus 31 times 3 times 10 to the 8 multiplied by 1 minus cosine 180, which we already know the value inside those brackets is 2. So we see up here 6.63 times 10 to the minus 34 divided by 9.11 times 3 times 10 to the 8 is 2.4259 times 10 to the minus 12. 2.4259056 times 10 to the minus 12. And we're going to multiply that by, 1 minus cosine 180, which we know has a value of 2, giving us a delta lambda 4.85 times 10 to the minus 12. The biggest delta lambda you can possibly get here in any of these questions is 4.85 times 10 to the minus 12, because cosine 180 maximizes that value. Did the initial wavelength matter? Back to the original question, did the initial wavelength matter? Where did it appear? Where did it appear in that equation? Nowhere. Didn't matter at all. Biggest we can get, if it comes back exactly opposite at 180 degrees, the biggest we can get is 4.85 times 10 to the minus 12 meters for delta lambda. We're going to finish off our day today, and we're going to finish off our unit talking about the wave nature of particles. What do I mean by that? Well, if you think back to the beginning of this unit, we talked about the wave nature of electromagnetic radiation. Remember the wave properties of EMR were refraction, diffraction, interference, and polarization. And we spent most of our unit talking about the wave nature of electromagnetic radiation. But then we went on to talk about the photoelectric effect and the Compton effect, both of which provided us with evidence for the particle nature of EMR. Well, we now say that EMR has a wave-particle duality. It has properties of waves and has properties of particles. Fast forward a few years to around 1930, and a guy named Louis de Broglie, a French guy who looks like it's de Broglie, but it's actually pronounced de Broglie, he suggested by symmetry, in physics, we've seen this before, physics is a pretty symmetrical subject. When A causes B, then B will often cause A. He suggested by symmetry that if things that we have always thought of as a wave, like light, can have a particle nature, in other words, if waves can have a particle nature, then why can't particles have a wave nature? So he made an argument based on symmetry that particles like electrons have a wave nature. They have a particle nature, just like Einstein didn't discount the wave nature of light, de Broglie didn't discount the particle nature of electrons. He just suggested there's an additional nature to it, a wave-particle duality. Particles like electrons have a wave nature in addition to the particle nature, and we can actually calculate the wavelength of something like an electron. We won't, because we don't have to do that in Physics 30, but you can, and it's pretty easy to find, actually. We just won't bother because we don't have to. We say particles like electrons have a wave nature, but particles like baseballs have a wave nature as well. It's just that the mass of a baseball is so big compared to the mass of an electron, its wave nature is effectively not there. We talk about the context of wave-particle duality of things like things with mass. We talk about things with a really, really small amount of mass, like electrons, other subatomic particles. But here's the thing. When he came up with this hypothesis, the de Broglie hypothesis, there was no evidence whatsoever to prove that he was right. It was an argument based purely on symmetry and mathematics, which, hey, sometimes that works for us. But we always like to find evidence. We always want to find proof to show that that symmetry argument or that math argument is correct. Well, evidence did come later on, but not right away. Evidence did come later on through what we call electron diffraction experiments. And what do we mean by electron diffraction experiments? Well, we spent a few days earlier this unit talking about the diffraction and interference of light. When light goes through two openings, it diffracts, it spreads out, it interferes, and then it produces a pattern: bright spot, dark spot, bright spot, dark spot. Thousands of experiments have been done in the last 75 years showing us that, in fact, electrons, under the right circumstances, will produce the same interference pattern as light. In other words, bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. And that's not what we would expect to see with particles. But we do with the electrons under the right circumstances. So there must be a wave nature of those particles. If they exhibit wave properties, in other words, they diffract and interfere, then they must have a wave nature.